Okay, now we're moving on. We just finished with question 9. So let's take a look and see what is coming up next. Hopefully you're able to find the chemical formula for glass in section 6.3. Number 10 is a question on accuracy versus precision. You may remember a pre-lab where we talked about that in our hydrate lab, where we talked about throwing darts and accuracy versus precision. So you can find those in your notes. If not, look up the definition. And again, a little more homework for you to do. It's not going to do you any good to have, hey, this question's about accuracy and precision if you don't know what the difference is. Okay, the dartboard and Homer are a little reminder for you of where to find this. Okay, take time to get this all written down because this kind of goes a little bit beyond our textbook, so I will take care. I think this is really important stuff. So write that all down and then I'll go through and explain it. Pause. All right, so hopefully you kind of got the gist of this as you were looking at it. Let's say you wanted to take water which normally boils at 100 degrees Celsius and change its boiling point. One of the things you can do is add like a gas and make it bubbly water, carbonated water would have a different boiling point, or a solid solute like salt. If you add those things, the boiling point will increase slightly. And it's kind of the same reason you put salt on the ice on your sidewalk. The reason you do that is the melting point goes down. Well, the boiling point, interestingly enough, goes up when you do that. It's called boiling point elevation. Some people believe that's why you put a little bit of salt in there, and then the water will boil at maybe 101 degrees. And it really, honestly, is not going to make that much difference. I think we actually calculated in order to go up just a few degrees, you'd need like a cup of salt in a normal sized pan of water for your pasta. So, but anyway, that will do it. Now, also increasing the pressure will really get that boiling point to go up. A pressure cooker, they're kind of all the rage now. To get a pressure cooker cooks your food a lot faster, because if you keep that pressure, the boiling point can really shoot up. You can get a lot higher than 100 degrees Celsius in there. And then also if you decrease the pressure, the boiling point will go down. An example of this is water boils at about 96 degrees in Denver, Colorado. And sometimes they even put special cooking instructions. You have to cook it a little bit longer at high elevations because the water just doesn't make it up to 100 degrees because there's not as much pressure pushing down. And that's what boiling is when the liquid overcomes the atmospheric pressure. So if you got that, you're in pretty good shape with number 11 with these definitions. Now, number 12, I really want you to look back over those manometer problems. There is a book section, 13.1, where they talk about those. But if you go back and look at our worksheet, I was putting a lot of check marks where everybody just did all 4 problems with the open manometer problem, just like the example problem. But remember, the levels can be like this or like this. And in one case, you have to add to the atmospheric pressure, and in one case, you have to subtract from the atmospheric pressure. So if you think of those two levels, if the level right here by my head is the gas, okay, so here's that bulb, and this level is lower, then this pressure is winning, right, on this hand right here. That one's winning, so it's higher. So it has to be higher than the air pressure. If the air pressure was 92, you would have to add it to the air pressure. Now, if the one by my head was like this, then over here the air pressure would be pushing harder than the gas by my head, so then you would have to subtract it from the air pressure. I think a lot of us missed that, but make sure you look that over carefully, and just think of it as a battle between the gas, which is inside that little bulb, and that's going to push down, and then the air is also pushing. Who's winning? If they were equal, then the pressure of the gas would be the same as the atmosphere. So definitely worth looking this over. A lot of check marks on the back side of that worksheet when we went over it. So double check what you have there. Number 13 is going to involve some calculations. Remember, if you want to earn the curve, you're going to have to show your work on problems like this one. So you're given a gram amount of a gas, you're given a pressure in atmospheres here, and you're given a temperature. And you are asked to figure out what the volume is. So that has ideal gas law written all over it. PV equals nRT. So as we go through it, you can see we'll start with the pressure. Just put that right in there. Now, with the video you guys watched last Wednesday, they included the pressure units. That's totally up to you if you want to do that. It's just sort of another little angle that I decided to show you. So this little N right there stands for the number of moles. And you have to remember that the gas is diatomic. That's a big hint for this problem. And then I would list out the Magnificent Seven. That is when they are by themselves, they like to be diatomic. So make sure you have that list for this problem. And that's why we divided by 32.0 instead of 16. Now, in terms of atomic weights, you can go back to using your periodic table and rounding to one place. You could use your stoichiometry periodic table. If that's 32.00, it's not going to change the answer very much. So don't worry about that. That's just, again, a couple of different methods that we showed you. Since the gas pressure is in ATM, it's 0.0821 is what we used. This is an AP version. Sometimes and I get things from different sources, but that's basically 0.0821. You can use that in there, and of course you're converting the temperature into kelvins, and I think your book uses that number as well. That might have been why I changed that. So anyway, you plug that in, and you end up with 5.19 liters. Number 13 is going to be very similar to that, and you're not going to get the curve if I don't see this work. It doesn't have to be right, but hopefully it will be, because you have this good example to use. All right, and now for a quick break on a Wisconsin road crew. Wisconsin joke. All right. Number 14 is a percent composition problem. Piece of cake. Circle, square, method. All right? Take the circle over the square, and you can get the percent of any element that you want. Okay? That one's real straightforward. You all did real well on that, on the mole test. So Moving right along. Hit the pause if you need to get all those numbers written out. Good to have an example. And then we move on to number 15, stoichiometry. The goal is the mole, and remember the definition, mole to mole conversion using the coefficients in the balanced equation. This is our very first type of problem. This one is, so here's that, just to use an equation that we just talked about, which is the combustion of butane. How many moles of oxygen are required to produce 12.5 moles of carbon dioxide? And assume an excess of propane. So this is real straightforward. It's a one-stepper. It's that mole-to-mole conversion. Now, I want to walk you through this because there's a handful of us that were flip-flopping the mole-to-mole conversion. Now, if you do this right, it's very difficult to make a mistake because moles of CO2 were what were given for you, and guess what goes on the bottom here? Moles of CO2. So you should not be flip-flopping those. You have to have that in order for those to cancel out. And then moles of what you were looking for, which was oxygen. They want how many moles of oxygen would be needed to make that many. That's what goes on top. And now you use the coefficients in the balanced equation, and you're not going to mess them up because the 3 is in front of the CO2 and the 5 is in front of the O2, and then you just take your calculator and you do a little math, and you get 20.8 moles of O2. Yeah, that's simple, okay? Pretty straightforward. All right. How about a Wisconsin diner? You ever been to this place? Uncle Dad's? We treat you like family because you just might be. It's right across the river. It's nice. They got good burgers. Number 16 is going to be a mass volume stoichiometry problem. So this is sort of brand new, but it's going to involve the mole wall. There he is, 1 mole. There's the STP stickers, the 22.4 liters. So, here's the problem. Write it down. Okay? And hit the pause, and then I'll walk you through it. Okay, so this, as you were writing this, we see that, you have one number to start with, so that's 53.5 liters, and then you put the 22.4 liters right there. Well, that's where you need that STP mole wall. You know that 1 mole is 22.4 liters. Well, guess what? You have converted it into moles. See the moles of CO2? Put it right there. What am I looking for? How many grams of carbon? You put that right there. 5 moles of carbon. And then we go over to this side, and the moles of carbon, and don't use the coefficients in any step. A lot of people were putting a 5 there because it was the only time you use the coefficients is in this mole-to-mole conversion. Remember, 1 mole. There's 1 mole over on the periodic table mole wall as well. So you got 12.0 grams of carbon, 1 mole of carbon. You multiply the top numbers, divide by the bottom numbers, you get 143 grams. The coefficients are only used in the mole-to-mole conversion. Okay? There is 1 mole on each wall. All right. And if you want to read about that, that's 13.10. But number 16 is going to be dangerously close to this problem. Okay? So, you are now certified to take part 1 of the ACS Final review tomorrow. Good luck. Get some really good notes.